Hello, my name is Desmond Edegisi, and I'm here to take us on the subject mathematics. Today, we'll be learning on the theme numbers and numeration. And under numbers and numeration, we'll be studying sets. Our topic for today under sets is types of sets. We're going to learn about the different types of sets that we have. Let's go into our class. Today, I expect us at the end of our class to have learned about the universal set. Also, I expect we must have known what the empty or null set is all about. I expect us to be familiar with what is referred to as infinite sets. Next, we'll also learn about the finite sets. At the end of our class, we must have learned about what a unit set is, and finally, we would come to know what number sets are. Let's go into our class. I guess you are raring to go. First, we'll be looking at the universal set. The word universe, it means something that contains a lot of other things. That is exactly what the universal set is. It's a set that contains all of the elements under consideration in a given problem. That's what our universal set is. It has a symbol which is known as or pronounced as the xi. It's a Greek term. It may also be shown as a symbol here, which represents the universe. Our xi is also referred to as the entity. Either of these appellations are useful in the description of our universal sets. Let's take an example of what a universal set is all about. If we have, for instance, our set A, which is a set of pear and apples, and we have another set B, which is the set of mango, orange, and purple. If we looked at both of our sets, we'll see that we have pear, apple, mango, orange, and purple in both sets. The universal set is a set that contains all of the elements of both sets in consideration. So we have pear in the universal set, we have apple in the universal set, we have mango in the universal set, we have orange in the universal set, and we also have purple. So our universal set is the set that contains every element under consideration in a given problem. Let's take a look at an example. Then we will understand better what the universal set is. Take this example. The universal set here is the set of all the months in a year. I guess you know there are 12 months in a year. And of course, they range from January to December. Now we have three sets here. The first set being set J. J is the set of all months that begin with the letter J. While A is the set of all months that begin with the letter A. And M is the set of all months that begin with the letter M. If we were asked to list the members of the set, let's do a list quickly. So J would be, our sets of J would be January, June, and July. The set for A would be the months April, August, April and August, while our sets for M would be March and May. Now, if we notice the elements of our three sets here, January, June, July, April, August, March, and May, they are all also elements within our universal set which contains all of the months within a year. So our universal set is the set that contains all the elements in consideration in a particular problem. Let's take a look at this other example to see if we understand correctly what the universal set stands for. If the universal set here is the set of pear, pineapple, cashew, and orange, which of the following statements is correct? The set of cashew is an element of a universal set, or cashew is an element of our universal set. Well, from what we've explained about what the universal set is, we said it's the set that contains all the elements and not sets. So cashew here is an element, while our first option here is a set of itself. So the set of cashew would be a subset of our universal set. And of course, in our class to come, we will learn about what a subset is. But in this class, we will not learn about subsets. Therefore, our answer here would be cashew, which is an element, yes, of the universal set. So cashew is an element within our universal set. And of course, the second option is our correct answer. Next, let's take a look at this example here. We said given the universal set of the range of numbers from 1 to 10. N is the set of all even numbers, while F is the set of numbers divisible by 5, and G is the set of numbers greater than 3. If A, which is the quantity we seek to find, is a number such that A is an element of N, A is also an element of G, A is an element of our universal set, and A is an element of our set F. What is A? Let's take a look at our given parameters, again. A is an element of N. It means that A is an even number. Let's list out our given sets here. N is the set of all even numbers within our universal set of range 1 to 10. So even numbers within the range 1 to 10 would be the elements 2, 4, 6, 8, and 10. F is the set of numbers divisible by 5. Of course, there are just two numbers within our universal set that are divisible by 5, and that's 5 itself and 10. Next we have G, which is the set of numbers greater than 3. So we have our numbers, as 4, 5, 6, 7, 8, 9, and 10. So now we have our sets written out. Let's see where our parameters fit in. If A is an element of G, it means that A again is either 4, 5, 6, 7, 8, 9, or 10. If A is an element of our universal set, it means that A is between the range of either 1 to 10. And finally, if A is an element of F, it means that A is either 5 or 10. So we have a range that is far broken down to just between 5 or 10. Let's see if 5 can be gotten. If we check our list here, we have no 5, we have 5 here, we have 5 here. So we cannot have 5 because 5 must be a common number within our three sets. The other number we have is 10. We have 10 in our set N, 10 in our set F, and of course 10 in our set G. 10 therefore is the answer that we seek. A is therefore equal to 10, and that's our answer. Let's go on as we learn more about other types of sets. Another type of set that we have, which is a very peculiar set, is what is known as the empty set. The empty set also goes by the name null set or void set. The empty set is a set that has no elements at all within it. The empty set is written as an open and close curly bracket or 0 with a slash across it. Either of these two notations will tell us that our set is empty. Let's take a look at some practical examples. The set of whole numbers less than 0. This is an impractical possibility. There are no set of whole numbers less than 0. Whole numbers are numbers that are above 0. That is, they are from 1 and above. They are also known as our counting numbers. Whole numbers may also be inclusive of 0, but not less than 0. Therefore, there is no situation like this. We say this set, therefore, is a null set. Let's take another example. Triangles with 4 sides. This is a very impossible situation. Triangles, as we all know, have 3 sides. So there is no triangle in existence that has 4 sides. It therefore means again that our set here is a null set. Let's take a look at a third example. Students in the university who are 5 years old. Wow. No one has ever broken such a record of having a 5-year-old in the university. Of course, the capacity of their brains cannot take the level of study necessary to remain in university. So this situation again is most probably non-existent, and hence we say our set again is a null or an empty set. Finally, let's take a look at our example here. Numbers divisible by 4 but not divisible by 2. This is again very much impossible. If we have a number that is divisible by 4, it therefore means that 2, of course, would also divide such a number. Therefore, once again, this example is an example of a null set. So we say all of these situations do not exist. Therefore, they are called empty sets. Let's go on to learn about more sets. Another set that we have are the infinite sets. Infinite refers to something that is uncountable, something that continues, that goes on and on. And hence we get the meaning of our set from. There are sets that have unlimited number of elements. We cannot count them. Let's take an instance. The set of all multiples of 2. Give it a try. You would have numbers like 4, 6, 8, 10, 12, 14, 16, 18. You would probably get tired and run out of breath because it is impractical to count the number of sets or the number of the multiples of 2 that we have. Therefore, such an instance is referred to be an infinite set. Another example is the set of A such that X is an element of N referring to natural numbers, where X is greater than 1. So all natural numbers greater than 1. Try to do a count. You have 2, 3, 4, and then you count up to 5 billion, 3 billion, get to a trillion and above. I guess you run out of breath. Again, you cannot count such a number. It is unlimited. And so we refer again to this as an infinite set. Once again, let's take another example. The set of all whole numbers divisible by 4. Divisible by 4. It's so much that we cannot do a count once again. Whole numbers divisible by 4 are so plenty that we refer to them as unlimited. Again, we will say this is an infinite set. Let's take this last example here. The set B, which is the set of all x such that x is an element of n, being natural numbers, and 2n plus 1 is greater than 1. Of course, this refers to an odd number. It means that The set is the set of all odd natural numbers greater than 1. All odd numbers that are natural numbers greater than 1. Of course, once again, we cannot do a count. They are uncountable or unlimited. And that's why we refer to them as infinite sets. Just a clue. Infinite sets are sets where we have to make use of our ellipsis. In most occasions, because we cannot do a count, we make use of the ellipsis to indicate that such a count is uncountable or goes on forever and ever. And of course, we said the ellipsis may be used within the range to indicate if there is a boundary. But of course, for unlimited numbers, there are no boundaries. So the infinite sets are used at the beginning of the list of our elements or at the end of the list of our elements, depending on negative infinite numbers or positive infinite numbers. Let's take a look at our next type of set here, which is the finite set. The finite set is the opposite of the infinite set. Finite, of course, refers to something that has an end. So the finite sets, they are sets that are countable. An example of a set that is countable is the set of all vowels in the English alphabet. Of course, if I asked you to tell me the vowels in the English alphabet, you will quickly tell me A, I, E, O, U. So you have 5 vowels in the English alphabet, and therefore we refer to such a set as a countable one, which is referred to as a finite set. Let's look at another example. The set of all colors in the rainbow. If I ask you to tell me the set of all colors in the rainbow, let's do a quick write-up. So we have red, orange, we have yellow, we have blue, we have green, we have indigo, and we have violet. So we have 7 colors within our rainbow. And of course they are countable, hence we refer to them as finite sets. Next, let's take a look at our other example here. The set of y, which is the set of all x, such that x is an element of n. N refers to natural numbers, where x are prime factors of 30. If we were to list the prime factors of 30, we would have 2, 3, and 5. Of course, this is very much countable. We have 3 prime factors, and hence we refer to this set as a finite set. Lastly, let's take a look at our set here. Set B, which is the set of all x, such that x is the range between 15 and 1. Or x is less than 15 but greater than 1. If we were to list this out, we'll write our elements of the set as 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Altogether we'll have 13 elements. 13 elements, and of course that tells us that our set is countable and therefore is a finite set. Again, let's take a look at another type of set we have. This set is referred to as the unit set. It's a unique set. Quite different because it contains only one element. Hence the name unit. It has just one element. So you have examples as the set that contains 0 as its element, the set that contains 2 as its element, or the set that has spoon as its member. All of these are examples of a single set. A single set is also known as the singleton. Singleton. Let's take a look at some examples to better understand all the sets that we've learned about so far. Now we have a list of sets we've been asked to decide which of these sets are either a finite set, an infinite set, or a single set. Promise to be an exciting exercise. Let's see if we exactly understand what single sets are, what infinite sets are, and what finite sets are. Let's start. The set of the number of hearts in a human body. The number of hearts in a human body. How many hearts does a human body have? A human body has one heart. So we'll write this set as 1. This set therefore is what? A single set. And of course we also call this kind of set a singleton. Singleton. Let's take a look at our second set. The set of x such that x is an element of W, the whole numbers, where the whole numbers are divisible by 1. Divisible by 1. Every number we can imagine from 1, of course, not 0, but from 1 upwards, they are all divisible by 1. So we are more or less listing all the numbers which we refer to as our counting numbers. Such a number is too large to comprehend or to count. And so we refer to this kind of set as what? An infinite set. A set that goes on and has no end. Let's take a look at our third example. The set of the letters of the alphabet. An alphabet, or the alphabet, sorry, has 26 letters in the alphabet. If we were to list it, of course, A, B, C, D, up onto Z, we have 26 letters in our alphabet. And so, since we have a countable number of elements, we refer to this kind of set as what? A finite set. Next, we have the set of numbers divisible by 5. The set of numbers divisible by 5. Wow. If we were to do a count of how many numbers that are divisible by 5, we'll probably lose count. There are so many. Once again, this number is uncountable. And that's why we refer to such sets as an infinite set. Let's take a look at our next example here. The set of x such that 1, or the set of x, such that x is a range between 3 and 1. Or x is less than 3 but greater than 1. The only situation that satisfies our statement here is the number 2. X has its element as the number 2. 2 alone is less than 3 and of course greater than 1. Since we have just one element within our set here, we'll call such a set a singleton. Next, let's take a look at our next set. The set of the prime factors of 30. If we were to do a list of the prime factors of 30, we would have the numbers 2, 3, and 5. So we have a countable number of elements within our set. And of course, since it's countable, we say this set is what? Finite. Next we have the set of the primary colors. The primary colors from our art class, if we remember, are red, yellow, and blue. So we have just 3 colors referred to as primary colors. Therefore, our set is finite. Next, let's look at our next set. The set of fractions less than 1 over 100. Again, such a set has an innumerable count, and therefore we refer to that as an infinite set. And lastly, the set of the multiples of 7. Once again, we have so many multiples of 7, beginning from 7 itself. 7 times 1 would give us 7, 7 times 2 would give us 14, and so on and so on and so on. So we have an infinite number of the multiples of 7. That's why we refer to such a set as an infinite set. So now we can easily decipher or distinguish between a finite set, an infinite set, and of course a single set. Let's go on to learn about other types of sets. Now we have some peculiar type of sets which we refer to as number sets. Number sets. In our introductory class on sets, we said set is a collection of anything, but for the study of mathematics, set is primarily a collection of numbers. Now, there are different categories of numbers that we come across when we study sets. One of that category of number we have is what we know as the natural numbers. It is written in boldface font as capital letter N. It is the whole numbers that range from 1 upwards. We also refer to our natural numbers as the counting numbers. That is, numbers that are useful in counting, beginning from 1, 2, 3, and above. The next set of numbers that we have are the whole numbers. The whole numbers contains all our natural numbers, inclusive of 0, which was not originally in our natural number. So, the set of whole numbers is the set that has elements 0, 1, 2, 3, 4, 5, and of course, to infinity. The sets of integers are our natural numbers, which we've already talked about, also known as our counting numbers that range from 1 upwards, negative whole numbers, numbers less than 0, that is numbers like -1, -2, -3, down to an infinite number, and 0. So the integer ranges from 0 up to all positive numbers imaginable and down to all negative numbers imaginable. So we have the set of integers as numbers that range from 0 down to negative numbers to infinity, and also upwards to positive numbers that go on forever. Our integers are a combination of the natural numbers, negative whole numbers, and 0. The next category of numbers that we have under the number set are what we refer to as rational numbers. It is written as a boldface Q, capital Q. Rational numbers are numbers that we get by dividing one integer by another. In other words, rational numbers are fractions. So a rational number Q is the set of all A over B such that A and B are integers and B is not 0. So A and B may be integers, but B is not 0. An example of our rational numbers are 3 over 2, which is a fraction. Of course, it is 1.5 in its decimal fraction form. 8 over 4, which is a fraction, and of course would give us 2. 136, for instance, all over 100 will give us 1.36. This is also a decimal fraction. So, our rational numbers are all fractions that we can imagine. The next category of number sets that we have are called the irrational numbers, and is written as a capital letter I in boldface format. Again, it is the opposite of the rational number. It is a number that cannot be written as one integer over another. Example of such kind of numbers are roots of numbers that are not perfect roots. A perfect root will be root 4, which would give us 2. Perfect root will be root 9, which would give us 3. A perfect root will be root 4, which would give us 2. A perfect root again will be root 9, which would give us 3. A perfect root again will be root 16, which would give us 4. But for roots that are not perfect, we have roots like root 3, root 2, root 5, root 7, and the likes. Another kind of irrational number is a number that we are very familiar with, the pi. The pi, of course, we know has value 3.142 and then a whole range of other numbers. The numbers of an irrational number are non-repeating, non-terminating decimals. So we have 3.142 and a whole range of numbers behind that if we study it carefully, we'll find that there are no repeating patterns within, and of course it is non-terminating, that is continuous and goes on and on. Irrational numbers are therefore the set of number x such that x is a real number that is not rational. That is, it is the opposite of rational numbers. Another type of number sets that we have are real numbers. Again, it is written as a capital R with a boldface font. All rational and irrational numbers combine to make up the real number. So a real number may be positive, it may be negative, or it may be 0. Examples are 1.5, which is a rational number, minus 12.3, which is a negative fraction. It's an irrational number. 99, root 2, which is an irrational number too, and our pi, which is also a type of irrational number. All of this make up our real number. In summary, we've learnt about 6 different types of sets. We've learnt about the universal set, which we said is the set of all elements under consideration in a particular problem. Next, we learnt about the empty or the null set, which we said basically is a set that does not exist. We learnt about the infinite set, which we said is the set that contains elements that are innumerable in measure and hence are considered infinite. Next, we learned about the finite set, which we said is a set that contains a countable number of elements. The unit set is a set that contains just one element as its member. Next, we learned about the number sets, where we saw numbers like the integers, our whole numbers, rational numbers, irrational numbers, real numbers, and the likes. With all of this, I'm sure we learned a lot. I'm glad I took you on this class, and it will definitely be a pleasure for me to see you in my next class. For now, it's bye.